Welcome back. Today's lesson is section 6.4, work. So when we look at work, we have distance in this direction, and we have distance in this direction. We want the area of that. We say y is equal to f of x, and we can integrate that, and that's the area, right? That was when we had area. Now we want work. Well, instead of distance going up and down, it's the force acting on it. We still have distance from left to right, and we still have a function y equals f of x, which represents the work being done. It's the area underneath that curve, and we can integrate again from a to b of f of x dx. And that's going to give us what we call work. So in this course, we're going to look at work with measurements in metric and in British. So when we're using the metric, force will be measured in newtons, and distance will be measured in meters. If you are given kilometers, centimeters, or anything else, you must convert it to meters. And if we're in the British form of work, we're going to have force measured in pounds and distance measured in feet. And again, if you're given yards or inches, we would have to convert those into feet. So here's a very simple explanation. It says work is equals the force times the distance. So we write W is equal to FD. The force in this instance is 10 newtons. And then we're going to multiply it by the 5 meters. It gives us 50 nms, Newton meters. And the common way of calling this is joules, 50 joules. So the work required to move this box here 5 meters to the right with a force of 10 newtons is 50 joules. Now, force needed to lift an object is a little different. When we're dealing in metric, we have to talk about the mass. Right? Object has a mass of m kilograms. The force needed to lift the object is equal to 9.8 times that mass. So mass does not include, when we're talking about moving this stuff, doesn't include the effect of gravity. When we're looking at the British units, it's the object of the weight, which is its mass, and the force needed to lift it is just that, the object's weight. We don't have to take into account gravity. So here we go. How much work is done in lifting a 20-pound weight 6 feet off the ground? Well, the formula again is work is equal to force times distance. The force is 20, 20 pounds. The distance is 6 feet. So the work is equal to 20 pounds times 6 feet, or 120 foot-pounds. Oops, without the S. 120 foot-pounds. And again, that's very simple. We're just lifting it straight up. We don't have to take into effect the work of gravity. That says, how much work is done lifting a 1.2 kilogram book off the ground? Well, we'll work is force times the distance. Well, force for us is 1.2, the mass, times the 9.8, the effect of gravity. And that gives us 11.76. So our force is 11.76. So we have work is equal to 11.76, and we're going to multiply that by the distance. The distance is 0.7 meters. We're going to work that out, and I get 8.2 joules. 8.2 joules. Or you could say 8.2 Newton meters. Again, either one it would be absolutely correct. I wouldn't take off anything on the test. If you give me Newton meters as opposed to joules. I will take off for not remembering to multiply by the 9.8 when we're in metric. So now suppose the force changes as we move along. So I have one force from here to here, and it's a different force from, say, here, from that point to this point. And then it's a totally different force again from here to here. Yeah, and the force is changing over and over and over the distance. This is where calculus comes in. I want to integrate this stuff. I want to integrate from A to B. All right. So what we're going to do is, since force is changing, it's not consistent. It's going to change over the distance. You know, I might hit a rough spot, or it might be a little bit of it might be just for whatever reason there's more resistance in moving this, or I may be able to move it faster for whatever reason. So the force is not going to be continuous. It's going to have a change in the force, but that force can be represented by a function. And then we could say, well, work in moving an object from some point A to some point B is represented by the integration of A to B of the function f of x dx, where f of x is equal to force at x. So this is the function that we're going to be using to solve these problems. And yes, you need to know how to do this. When a particle is located at a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. So we have an A to B of some f of x dx. All right. We know f of x, the force, is x squared plus 2x. Right. We know a is equal to 1, b is equal to 3. That's the distance I want to move. So I'm going to integrate from 1 to 3, x squared plus 2x dx. Because that's what we're supposed to do. And these are all in pounds. We're not having to worry about lifting anything up, so everything's fine. I'm going to integrate this x cubed over 3 plus x squared from 1 to 3. So now that I have that, I end up with 9 plus 9 subtract 1/3 plus 1, which gives me a total of 50/3 foot-pounds, or you give me 16 2/3 foot-pounds. Do not give me a decimal unless I ask for it. Do not give decimal answers unless requested. And I'm fine with this improper fraction. It doesn't have to be a mixed number. We don't. It's just very convenient, especially if you're doing this on your calculator. When you hit the math button for fraction, it gives you an improper fraction. So now we talked about how we're going to do that. Let's talk about Hooke's law. Hooke's law is the force required to hold a spring stretched x meters beyond its natural length. So beyond its natural length. So if the natural length is 20 centimeters or 20 meters, and I want to stretch to 30 meters, I'm stretching from 0 to 10 meters. So I'm starting at 0. And it's 10 meters beyond its natural length. K is, so f of x equals k times x, where k is a constant for the specific spring. Note, units must be in either newtons and meters or in pounds and feet. So here is an example. It says a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? So we don't know what that k is, but we do know that f of x is equal to some k times x. Note, 15 centimeters is equal to 0.15 meters. 10 centimeters is equal to 0.1 meters. We have to be able to convert these. So we know that the force f of x is 40 is equal to some k times, well, how far did I stretch it? Oops, I'm sorry, its natural length. I made a mistake there. Its natural length was, sorry, I make mistakes sometimes. Its natural length is 15 subtract 10, 5 centimeters. But I want it in meters, so it's 0.05 meters, right? I have it in centimeters. I want them in meters. So my x value, the distance, is 0.05. So I get k is equal to 40 divided by 0.05, which is equal to 800. So now we know that f of x is equal to 800 times whatever my distance is. We are going to integrate AB of some f of x dx. Well, we know f of x. A, we want to go from 15 centimeters to 18, so it's 15 subtract 10.05 meters. 18 subtract 10, which gives me 0.08 meters. So now we know how far, because remember, we have to convert these from centimeters to meters. So now we're going to substitute our values in. We're going to go from 0.5 to 0.8. Our function is 800 x dx. And again, 8.05 meters. B is 0.08 meters. So now that we have this, we'll integrate. I get 400x squared from 0.05 to 0.08. I get 400 times 0.08 squared, subtract 0.05 squared, or 1.56 joules. And again, you can write 1.56 Newton meters, and they're both acceptable answers. Let's look at the next problem. And again, this is the first problem. The force, boom, and we worked it out. So here's the next one. It says a spring has a natural length of 20 centimeters. If a 25 Newton force is required to keep it stretched to a length of 30 centimeters, how much work is required to stretch it? So, again, we know that 10 centimeters is equal to 0.1 meters. We know that f of x is equal to kx. We know there's 25 newtons is the force, k. It's going beyond its natural length by 0.1, right? Because it's stretched to 30 centimeters, so it's 30 subtract 20, 10 centimeters, or 0.1 meters. Again, the conversion. K is then equal to 25 divided by 0.1, or 250. So the force, the function f of x, is equal to 250 x. So here we go. Now I have a function. I now care about the 20 centimeters to 10 centimeters. Well, I started at 20 centimeters, so my a has to be 0. My b is I'm going to stretch it 5 more centimeters, 0.05. But I have to remember that's in meters, not centimeters. So I'm going to integrate this from 0 to 0.05. Again, the place students are going to make the most mistake is forgetting to convert. Now that I have this, I can integrate 125 x squared from 0 to 0.05. I get 125 times 0.05 squared, subtract 0, which gives me 0.31 joules, 0.31 Newton meters, or if you wanted to give me it as a fraction, 5/16 joules. So let's change this up a little. Instead of the work is required, this time we're going to say if the work is required to stretch a spring 1 foot, so now we're in feet, beyond its natural length is 12 foot-pounds, how much work is needed to stretch it 9 inches beyond its natural? So we know that f of x is equal to kx. So we know that AB of f of x dx is the function we want. Well, we don't know x and k because we only know some information. So we know we're going to go from 0 to 1, some kx dx, but we do know that that's equal to 12 foot-pounds. Right? So it's the work required to stretch a a spring 1 foot beyond its natural length. So we're trying to find out the function. So I integrate the left-hand side, and I get k over 2x squared from 0 to 1 is equal to 12. I substitute the I get k over 2 times 1 minus 0 is equal to 12. K over 2 equals 12, where k is equal to 24. So now we have our k. So we know that f of x is equal to kx, which says f of x, we have k, 24, x. Now we have a function. So now we go back up here and see what we want. We want to go 9 inches. So 9 inches is 9/12, right? Because we want to be in feet. We can say that's 0.75. So we want to go from its natural length to 0.75. The function is 24x dx, where I get 12x squared from 0 to 0.75. Now it's time to evaluate this. You should pause the video and work it out on your own. I get 12 is 0.75 squared minus 0 squared, which is equal to 6.75 foot-pounds. So that's all the stuff with Hooke's law, and you should know Hooke's law for the test. There will be a problem on the test where I will ask about Hooke's law. I am not going to give you that formula, so you need to know how to do it yourself. You need to memorize that. So here's another problem. It says, look, I have a heavy rope. It's 50 feet long and it weighs 0.5 feet per pound. So there's a weight per pound. All right, per foot, I mean. There's a weight per foot. It hangs over the edge of a building. It's 120 feet tall. So I drew it out. I have a 120-foot building. My rope is from 0 to 50. And I'm choosing to make it oriented that 0 starts at the top and I go down to 50. I want to pull half the rope. So I'm going to take the first 0 to 25, and I'm going to pick all that up from here. All this is going to go up here and lay. So now I'm going to have this much rope, 25 feet. And then I'm going to have this much rope, 25 feet. Right? So this part of the rope the force is changing because not all of the rope is being pulled the same amount of distance. The distance is going to be 0 for the part of it. 5 feet of it's going to go up 5 feet. The 10 feet part is going to go up 10 feet to get on top of the building, and that's it. Now the second half of the rope, this 25 feet, it's going to get lifted straight up. So there's not much to do with that. So here we are. We're going to work out this problem now. I just need to talk a little about what's going on. So here's the setup. I'm going to go from 0 to 25 because that's how much it's going to go up. The rope weighs 0.5 feet of 0.5 pounds per foot. So there's my function, dx. So here is the top half of the rope. But then I have the second half of the rope that has to get added to that because there's force. Well, it's 25 times 0.5. That's the force, right? The weight of the rope, force, right, is the weight of the rope times its length. Well, there's 25 feet of it, and each foot weighs 0.5. So that's the mass of that rope. So that's the force I need. Then I need to go a distance of 25 feet. Right? So the work is force times distance. My force, again, is the length of the rope, 25 feet, times its weight, 0.5, because each foot is worth 0.5 pounds. and this is the bottom half of the rope. What's in black, it's integrated. What's in red doesn't have to be integrated. So I get 0.5x squared divided by 2 from 0 to 25, plus, doing the math on the right-hand side, what was in red, that's 312.5. Evaluating the left-hand side, I get 156.25 plus 312.5. I sum them together, and the work to lift this rope halfway up the building is 468.75 foot-pounds. And again, I have to evaluate it for half the rope going completely onto the building. So I have to integrate that part from 0 to 25. And the bottom half of the rope gets lifted straight up, so the work to lift something straight up is just the distance times its mass. And the mass was its length, 25 foot of rope, times it weighed 0.5 pounds per foot. That's why I had to multiply that all out together. And then I integrate it. Here's another problem similar in nature to that. This time it says I have a cable that weighs 2 pounds per foot. It's used to lift 800 pounds of coal up a mine shaft 500 feet. Find the work done. So this time I'm going to set it up a little different. I'm going to go from 0 to 500 because all 500 feet of that cable has to be wound up. I am told that the cable's 2 pounds per foot, so it's 2x. But this time, I'm going to say that I have an 800-pound coal. Because the coal is being raised from 0 to 500 feet, I'm going to choose to integrate it this time. And you'll see that whether I integrate it or don't integrate it, it works the exact same thing. So I'm doing this because, yes, since this is moving the same distance. I'm pointing this out because I have students who like to do it this way as opposed to breaking it up in two. If I broke it up into two, I would have to have, I would have done from 0 to 500 of 2x dx plus 800, because that's its weight, times its distance, 500, which turns out to be x in this problem. So we're going to integrate this. I get x squared plus 800x from 0 to 500. And that turns out to be 650,000 foot-pounds. And again, if I did that or I did this way, I'd end up with 2x squared from 0 to 500 plus 1, 2, 3, 4, 400,000. And I get the exact same answer. It doesn't matter. I'm just trying to show you that there's more than one way to look at these problems. All right, so we're doing pretty good. We've gone about 23 minutes into this video, and we have about 3 or 4 slides left. And these problems are problems that seem to trouble students on the test. So I want you to just pay attention on how to break them apart. So it says a tank has the shape of an inverted circular cone with height 10 meters and a base radius of 4 meters. It is filled with water to the height of 8 meters. Find the work required to empty the tank by pumping all the water out of the top of the tank. The density of the water is 1,000 kilograms. So I need to know that. So as I'm looking at this, I have a circle here with a diameter, with a radius of 4 meters. And they're all concentric circles, right? They're just area of a circle stacked upon each other, but they're getting smaller and smaller. The problem is I don't know this radius here. But if I look at this and I draw it on the right-hand side, which I've already drawn, 10 meters high, The radius is 4. I don't know that r. This is the r I don't know right here. If I move down x units, then the height of this triangle here, which I'm going to highlight. So I'm going to look at this triangle here, is 10 minus x. Then I have another triangle, which is the yellow and the blue together, which is 4 by 10, 4 over 10. So I can think of it as, if I want to set this up as a ratio, I could say r over 4 is equal to r over 4, right? R over the 4, the base of one triangle over the base of the other, is equal to the height of the one triangle, 10 minus x, over the height of the larger triangle, 10, right? This is small base, large base, is equal to small height, large height. I'm just setting up a ratio. But this allows me to get r in terms of x. After I do all the manipulation, I find that r is equal to 2/5 times 10 minus x. So now I have a way to represent each of these concentric circles. All right. So the volume of each one of these circles is pi r squared times h. Well, h is the thickness for delta x. Pi is still pi, but now we know what our radius is. It's this. So I'm going to have to make some room here. I have 2/5 times 10 minus x, all that squared, there's my r, times my delta x. And we know that work is equal to force times distance. All right. So we have the volume. Volume is equal to pi r squared h. Excuse me, sorry. Unfortunately, I can't edit out my sneeze. So we need mass. And the mass has to deal, going back up here, to the density of the water. So the mass is now 1,000 times 2/5 squared is 4 over 25 times 10 minus x squared, delta x. Now our force, right, our work, sorry, is the 9.8, right, because this is all in metric, so I need to have the force of gravity, and the distance. So now it's time to evaluate this. I have 9.8 times 1,000 times 4 over 25. I'm going to integrate. Well, where am I moving? What's interesting is I'm going from here, that's 0, that's 2, and that's 10. So my x is ranging from 2 to 10. So I'm looking at my x going from 2 to 10. Then I need to have where it's moving. It's moved. My x is moved. There's my x, right? That's the x getting out. Each one of the x's. Then I need my volume or my mass, right? Because I need distance for that. So that's 10 minus x 20 squared dx. So this is the x of it going out. This part is the volume and its mass. Remember, work is f of x dx. So I now have 1568, if I had a calculator, 2 to the 10. Expanding this on the right-hand side, I have x cubed minus 20x squared plus 100x dx. I can then integrate that. 1568 times x to the fourth over 4 minus 20 over 3x cubed plus 50x squared. And I'm going to evaluate that from 2 to 10. I'm going to let you pause the video now as you calculate it. And when you come back, I'll have the answer for you. All right, hopefully you've done this on your own, and you should get the answer of 3.36 joules. Because remember, we're in metric, not British. As you can see, the answer is 3.4. 3.4. I got 3.6. 3.36. Okay, I have 3.36. They have 3.4 because they rounded to one less. It's the same answer. And I'll tell you how many decimal places to give you. Here's another problem. It's the same basic thing, but this time I have to look at a different way of creating my slices. So what I want to think about is I have this sliver here. And if I do that, I have slabs. And each one of those slabs has their own volume. So it's the volume for that is length times width times height. But the problem is that the width is changing. This is one width, and this is a totally different width because it's getting narrower and narrower. So I'm going to do the same thing I did before. I'm going to set up ratios. I'm going to set up a large triangle inside another triangle. I know I'm going to move x units down, giving me the small triangle here would be a height of 3 minus x, where the larger triangle has a height of 3. So I'm going to say w over 3 is equal to 3 minus x over 3, or w is equal to 3 minus x. So now I have this width. We said volume is equal to length times width. Well, here's my length, so volume is equal to 8. My width, 3 minus x. My height is at delta x, because it's the thickness from here to here, delta x. Right? We're going to make the slabs almost invisible, so it's a delta x. So now let's do this. My mass is 1,000 because it's telling me here that 1 cubic meter of water has a mass of that. So I have to multiply it by 1,000. 8 times my volume, right? 3 minus x, delta x. To find its force, I need to have the effects of gravity. Delta x. Now here, my x's are going to range from 0 to 3. So I'm going to put all my constants on the outside like I did on the other problem. Integrate from 0 to 3. I'd have the 3 minus x piece. But my x is traveling from here, as we talked about it before. My x is traveling from here up to here. But I need to come up and out of the spout. I have to go up another 2 meters. So my x isn't just traveling x, it's traveling x plus 2 meters to get out of the spout. In the previous problem, let's go back, there was no spout to go out. There was no spout to go out. It just came out to the top of this inverted cone, a cylinder, circular cone, and it just fell out. Here I have a spout that I have to go up 2 meters. I have to work my way out of that. So that's why it's x plus 2, not just x. And then I have a dx. So working this out, I end up with 78400 from 0 to 3, expanding on the right, x minus x squared plus 6 dx. So I integrate x squared over 2 minus x cubed over 3 plus 6x. So evaluating from 0 to 3. Hopefully you'll do this on your own, but if you don't, here's the answer anyway, 1.05 joules. But again, we had to worry about the effects of gravity because we are lifting something, and we're in metric, not British. We have one more example to go over. I'm mostly concerned in making sure you know how to find your slices on here. So again, we have slices. We want to slice this different ways. So we want to have little slices. But what we should notice is when we're slicing it, again, I'm getting these slabs. So the volume, again, is the same as last time. Volume is equal to the length times the width times the height. H is a delta x. My length is 8. I just have to figure out my width. My width is changing, right? I have one width from here to here. I have another width from here to here. But the good thing is it's a semicircle. So if it's a semicircle, the radius is 4. I know I have a diameter, which I have highlighted in yellow, is 2. If I drop another diameter down, it's also 2. And then I could find I have a triangle, and I have a height of x, and I have this h I need to find. So what I have now is a right triangle. And I could say that A is equal to the square root of 4 minus x squared. But A is only half of my width, right? W is equal to 2 of those A's. So W, my width, is equal to 2 times 4 minus x squared, right? Because I only found A. I wanted all of this, the entire width. The triangle only gave me the base, which only gave me half of that width. So volume is equal to 8 times 2 times 4 minus x squared delta x. The mass, we're now in we're in British, 62.5. So mass is equal to 62.5, because I need that, times 8 times 2 is 16, and the square root of 4 minus x squared delta x. Well, here, I'm going to go from the bottom here to here, which is from 0 to 2. So my x's are going to range from 0 to 2. I'm going to put my constants on the outside, like I've been doing. 62.5 times 16. My x is going to travel from here to here, but then it has to go a foot out, so I have to add that 1 to it. Remember, we did that in the last one. If I have a spout, I have to add that distance to my x. So it's x plus 1. And then I'm going to multiply that by the square root of 4 minus x squared dx. All right, I will let you work this out, and I will give you the final answer. So here you can pause the video, and when you come back, you'll see the answer. So the final answer is 5.8 times 10 to the third foot-pounds. That concludes this lecture and everything that we need to know about work. You will need to be able to slice up these problems, and you will have a problem dealing with a spout on your test. I can pretty much promise you that. So this section, we've learned a lot. We learned Hooke's law. We learned that we had to, if we're lifting something and it's in metric, I have to account for gravity. If it's in British, I don't have to worry about the gravity. The mass is the mass. I don't have, for the force to lift it, I don't, it's just its mass. If the force to lift something in metric, I have to add gravity. For that force, if it's lifting straight up, we have to be able to integrate these. I promise you this problem or this problem, something, one of these two slices, knowing how to do that. And I won't give you these numbers. It'll be something different. So you definitely need to remember, figure out how to find that ratio. Finding this ratio, that's why I'm showing you this. Finding these ratios are really important. You know, finding all these ratios is very important, you know, and then being able to convert it. I'm not going to tell you I'm going to have one in British or in metric. You'll probably only have to do one, but there's not a lot of problems on the test. There's probably 12 to 13 problems. So saying I will just throw one problem out is giving up a lot of points on the test. All right, well, that concludes our lesson for today, and hopefully you'll have some questions for me when I see you in class. This also concludes everything that we need for the first test. Your first test will be section 6.1 through 6.4. We do not cover section 6.4 anymore, so you don't have to worry about section 6.5. If I said 6.4, I apologize. We're only covering section 6.1 through 6.4. We no longer cover section 6.5. And this is everything you need for your test. Thank you.